Hello there, everyone. We're delighted to share our system design and some of our experiences participating in this VPC 24 here. And many thanks to the organizers for providing excellent tools and environment and baselines for the reference of all teams. As you know, speech anonymization plays an important part in protecting the privacy of an individual in digital communication scenarios. And actually, it is not that difficult if you focus only on privacy. For example, by using a straightforward ASR followed by a TTS, we can completely reconstruct the speech, thereby erasing any trace of the original speaker's identity. However, if we consider the need to retain the original speaker's style and emotional characteristics to better convey information beyond the text, things will become challenging. So the VPC24 underscores this specific task in which we are required to balance the performance of three metrics, namely EER for privacy, UAR for emotion, and WER for content. These have been designated as the evaluation criteria. So why is there a trade-off? And this is important. We believe the creation of pseudo-speakers represents some inherent sparsity, and this is actually somehow a mismatch problem, a mismatch between training and inference. This issue is, from our perspective, particularly pronounced in the context of zero-shot emotional transfer in TTS, where it could be really difficult for emotion and speaker to be fully disentangled. So, when we attempt to transfer emotions to a non-seen speaker, we often encounter something like this. Either the emotion transfer is inadequate, or there is residual timbre information. So we understand some LLM-based TTS methods can relieve this, but hundreds of thousands of hours of speech data are required. The above problem are actually some common problems of synthetic models based on neural networks during transfer learning. And on the other hand, if we consider some methods using DSP, they often succeed in preserving emotional information by directly adjusting pitch, spectral envelope, or time scaling maybe, but they tend to fail in anonymization, and the generated speech may also sacrifice basic quality through a non-vocoder synthesizer. So if we consider introducing some anti-spoof, some detection systems maybe, these DSP-generated voices will be considered as fakes and thereby of little practical use. So back to this paper, we have conducted some explorations to alleviate these trade-off problems. We base our approach on a fully end-to-end voice conversion model where we achieve the purpose of changing speakers. In terms of modeling emotions, we use external emotion encoders to help train the acoustic model. Beyond voice conversion, we introduce a model fusion method to create pseudo-speakers to perform privacy protection. Here is our backbone. The content encoder is an ASR model of hybrid CTC and transformer, through which we extract the features from a certain bottleneck layer, and the features are often called PPGs, as you know it, for phonetic posteriorgrams, and this part is the emotional feature extracting module. We leverage a wave-to-wave based emotion encoder pre-trained on a dataset called MSP podcast. And the fundamental frequency F0 also helps in modeling emotion. To eliminate residual speaker information in emotion encoding, we connect a classification module from the gradient inversion layer to the speaker encoder, following the encoding layer. Since the training objectives on both sides of the inversion layer are opposed, higher classification accuracy would indicate that the emotion encoding before the inversion layer contains less speaker information. As you know, this is a common approach used to enhance disentanglement capability. And for the acoustic model, we adopt the same architecture as VITS, utilizing a combination of prior and posterior encoders to jointly model the speaker, emotion, and content. Subsequently, we employ a pre-trained hi-fi GAN as the waveform generation module, the vocoder. To enhance anonymization while minimizing the sacrifice on emotional preservation and content consistency, we aim for our pseudo-speaker construction process to avoid introducing training inference mismatches. So, we came up with the method of model fusion. We noticed that models of the same structure could sometimes be combined or summed together at the parameter level, that we could directly perform summation operation on the parameters within each node of the models, as the picture shown on the left. Here is what we actually do. Assume that we have a nicely trained VC model, and we fine-tuned cautiously with single speaker data to get several single speaker models. After loading each model, we sum all the node weights involved in the inference process in the model network according to a certain ratio. The weights, the ratio, are randomly generated and they are guaranteed to sum to 1. When we infer with the new model, the generated speech timbre will sound like an in-the-middle person among multiple fused speakers if the fusion weight is not a one-hot vector. These generated pseudo-speakers will make contributions in interfering with the ASV systems, and through this method, we can lightly and effectively create a large number of pseudo-speaker models, even when there are only a few available speakers with sufficient high-quality emotional speech data. Meanwhile, each pseudo-speaker is equipped with a corresponding neural network and weights, so this approach can somehow eliminate the mismatch of unseen speakers and can ensure that the acoustic model and hi-fi GAN produce fewer recognizable pattern artifacts. Next, we'll shortly outline the performance of our system. In terms of emotion preservation, we outperform other baselines except for B2. This is expected as B2 employs a DSP approach, resulting in comparatively minor modifications to the emotional features of the original input speech. We reach an intermediate level among the results of various baselines with regards to WER, though. We acknowledge that a slight increase in WER may be unavoidable, particularly with the introduction of unsupervised emotional modeling like Wave2X or global style tokens known as GST, which can potentially distort the content due to some conflicting interactions between content and emotion. This parallels everyday communication scenarios where you may find strong emotions could sometimes even make a little change to pronunciation, and such a phenomenon is more obvious in a tonal language such as Mandarin Chinese or Swedish. And considering privacy, we achieve some capability with an EER of more than 30%, and without model fusion, the EER performance will drop by nearly 8%. And we're surprised to find that simply by replacing the emotion features of Wave2X with GST, EER will also significantly decreases. We speculate that the style information of GST may contain too many speaker characteristics that are difficult to filter out, and it causes the clustering effect of different utterances in the speaker space to become severe after model fusion. Or, in other words, the utterances of the same source speaker can find more commonalities despite our fusion approach. Anyway, our system still have some limitations. Say we cannot mathematically or confidently know how the model fusion functions inside the inference stage and whether it really disrupts the discrimination ability of ASV systems. And our emotional modeling remains inadequate, leaving room for enhancement in emotion transfer effectiveness, especially for the emotion label of sadness. And this is all. This is the introduction to our system. Thank you for your attention.